So here's what we got. We're taking a block and we push it in. It's attached to a spring and we're pushing it in at 0.15 meters. The block weighs, or has a mass, I can't say weighs because weighs is a force and mass is different from that. The block has a mass of 1.2 kilograms and the spring constant is 1.0 times 10 to the 4th Newton per meter. Do you understand this idea of the spring constant? It's basically measuring the toughness of your spring. Like, for example, if I had a car axle, or not a car axle, but you know, like the spring in a car, the shocks, those things are huge springs. That has a huge spring constant. Maybe, I don't know what it is exactly, but it's bigger than that. Does that make sense?
Yeah.
Or if you take the spring out of your ballpoint pen, out of the cap of the ballpoint pen, it's got a very small spring constant, right? So if I move that a certain amount of meters, it's going to apply a much smaller force than if I move a car shock. Cool?
Right.
All right. So here's how you do these energy problems. Did I discuss with you the concept of what goes in must come out?
No, but I know I'm familiar with it.
All right. I regret to say that I haven't discussed with you energy then, if I didn't tell you about the concept of what goes in must come out. That's called the law of conservation of energy. It's basically saying energy cannot be created or destroyed. That's a pretty straightforward concept, right? You've heard that before.
Yeah.
What that implies, that's a huge implication though. That implies that all of the energy that comes in has to be all of the energy that comes out of the system. Are we cool?
Yeah.
Now, in physics, at least in this chapter, we're going to talk about very ideal systems. So we're not accounting for all of the energy, but we're accounting for, if I didn't have any kind of energy loss of this thing. So in an ideal system, what kind of energy does this block have at this very moment right now, when it's in this picture? There's 3 different kinds of energies, or 4. I guess there's straight up work, there's spring energy, there's kinetic energy, and I haven't taught you potential energy yet. So I'll give you a hint, it's not potential energy.
Wait, so spring energy is a type of energy?
Spring energy, actually, you know what? I take that back. It is a type of energy, yes. It is a potential energy. It's a special version of a potential energy. It is called, it's called elastic potential energy. Normally when people talk about potential energy, they talk about gravitational potential energy.
Okay.
Does that make sense? Boy, I should really go over potential energy in depth with you then. Let's do that today. Let's solve this problem, then we'll go over potential energy, kinetic energy, and I'll tell you the basic gist of everything. All right? All right. Spring potential energy, it has spring potential energy right here in this setup right here. This is while my finger's still on it before I let it go. Okay?
Okay.
Then what I like to do is I like to draw a picture. This is the before picture, here's the after picture. The after picture is saying, what kind of energy does it have? I account for everything over on this side. Now, let me read the thing again. It says, okay, I see. So, the after picture looks like this. This spring isn't attached to this block, so once I let it go, this block is going to start moving, and then it's going to keep going as the spring stops eventually. You know what I mean? So the spring's not attached to it, it's actually going to let it go. The question is, how fast is that thing going to be moving? What kind of energy does this thing have over here?
Kinetic.
It has kinetic energy because it's moving. It has spring potential energy over here, it has kinetic energy coming out. So what I'm saying is, in has to equal out. Or if I add up all of the ins, it has to equal all of the outs. If I add up all the energy going in, it has to equal all the energy coming out. All the energy going in is just the spring energy. That's all the energy that I see. So I have 1/2 kx squared. Cool?
Yeah.
And that has to equal to the energy coming out. What energy do you see that's coming out?
Kinetic.
1/2 mv squared. That's the equation for kinetic energy. We cool?
Yeah.
Alright. So, all you're asking me to do is solve for V. That kills that, that kills that. Divide this by m. Take the square root. So V is equal to the square root of kx squared over m. Then you just plug in your numbers. Is that what you got?
No.
It's probably because I didn't show you how to do this correctly. I'm sorry, that's my bad. Let's take a look at the units to make sure that the units work. The units of K is measured in newtons per meter, right?
Right.
The units for X is measured in meters, so that's a meter squared because I have X squared down here. The units for M is measured in kilograms. My question is this a secret, a secret message for the, for velocity? All right, well this meters cancels out with that meters, okay? And I have a newton times a meters divided by kilograms. So a newton is also known as a kilogram meters per second squared. Do you agree with that?
Yeah.
Because a newton is really just a unit of force equals ma. M is kilograms, A is acceleration meters per second squared. That's why I just changed N to kg m over s squared. We cool?
Yeah.
All right. This kilogram kills out with that kilograms, and you're left with meters times meters over second squared. That's also known as meters squared over second squared, but you're taking the square root of that whole dang thing, so you end up with meters per second. Hey, that's the correct units for my answer. So I'm thinking that that's the right expression. You just got to plug in the correct numbers. So you take 1 times 10 to the 4th, put it over here. You take 0.15 and you square it and put it over there, and you slap in the 1.2 kilograms, and then that will give you your answer, whatever the calculator says. We cool?
Yeah, sounds good.
All right, cool.